Hi guys. So today I'm going to show you another question. This question has a lot to do with really understanding how certain theorems or how certain proofs work, or how you should actually approach solving or proving whether or not a certain theorem is true. In this case, I'm going to present to you what is not so much of a theorem, but really more of a question, but which requires a proof if it's true. So this is a question. And the question is quite simple. It's just a true or false question. But of course, you have to prove whether it's true or false. So the question says let f be any function, and you are told that it's a function such that the limit as x approaches infinity of that function is infinity. So this simply means, for example, if you have a function as x grows very, very large, the value of the function also grows very, very large. There is no other condition. Like some functions that would satisfy this condition would be like y equals x, y equals x square plus 1, something like that. Anything like that would satisfy. Even none of x, for example, satisfies this condition. Um, and then it says that for all of these set of functions, so let's say that there's a set of functions, and this set contains all the functions that satisfy the condition that limit as x approaches infinity of f of x is infinity. And the theorem says that given that this is true, then is it also true that limit as x approaches infinity of sine of f of x will not exist? So just to give you a bit of an idea about why this question actually does make sense, is because let's say you said limit as x approaches infinity. Let's pick f of x to be x, for example, and we'll see that if this is the function, then this theorem is satisfied. So clearly, limit as x approaches infinity of f of x is infinity. This is trivially satisfied. The other one is, of course, limit as x approaches infinity of sine of f of x. So in this case, sine of f of x is just sine of x. And if you graph out sine of x, you get a function that looks something like this. And clearly, as x approaches infinity, this does not approach any given value. It oscillates between -1 and 1. And therefore, we can conclude that the limit does indeed not exist. Because remember, the limit does not exist means that either the limit is infinity or negative infinity, or the given function oscillates, it does not approach a single value. Or there is another way for the limit to not exist, which is in case of a jump discontinuity. So for example, in this case, the limit does not exist at this point. So once again, question is quite simple. You just have to argue whether or not the theorem stated above is true. If you think it's true, then you would have to prove that for every function that satisfies the condition that the limit as x approaches infinity of that function is infinity, this limit as x approaches infinity of sine of f of x does not exist. So at this point, I would ask you to just pause the video and see if you can figure out whether this is true or false. Okay, so I hope by now you have attempted this question on your own. And one thing that I would like to tell you before I present the solution to this problem is to realize that whenever you encounter any theorem or any proof or any question in any sort of your analysis class, never assume that that is true unless you have a proof for it. Um, I mean, if you just trying a bunch of different functions and seeing that a large number of functions satisfy this theorem is not sufficient to conclude that this theorem is true. I mean, otherwise it wouldn't be a question to begin with. In this case, in fact, this theorem is false. There is a function for which limit as x approaches infinity of f of x is infinity, but limit as x approaches infinity of sine of f of x also exists. So let me give you one function that will serve as a counterexample. So first of all, this theorem is false, or I would say, well, this theorem, yeah, of course, okay, this theorem is false. So a counterexample in this case. So here's the intuition behind the counterexample. What we really want to look at is the sine function. So if you look at the sine function, and if you look at the values of the sine function at different points, you'll see that it's a function that repeats itself. In particular, sine of n pi, where n is an integer, is always 0. So for any integer n, sine of n pi is always 0. So sine of pi is 0, sine of negative pi, 2 pi, 3 pi, 4 pi, and so on. It's always 0. So this is the idea that I'm going to use over here. What I'm going to say is that my counterexample is sine f of x. Now, of course, since this function is defined for all real numbers, I'm going to define it this way: sine of the floor of x times pi. What's the floor function? If you're wondering, like, what's this floor symbol? The floor function is the formal definition of the floor function, or the floor of x. It is the largest integer smaller than x. If you want to graph it on Desmos, you literally just write floor of x. So for example, in this case, for example, the floor of 2.5 is 2, because 2 is the largest integer smaller than 2.5. The floor of 4 is 4. The floor of pi is 3, and so on. So this is the counterexample. Let's see why this counterexample works. First of all, clearly, limit as x approaches infinity of the floor of x is infinity, because, well, as x becomes very, very large, the floor of x also becomes large. So for example, the floor of 3.5 is 3, but the floor of 1,000,000 is 1,000,000, and so on. So clearly this is true. There is a more formal way of proving this that would involve using the formal definition of the limit, but I'm not going to do that over here. Now let's look at this, the other one. So what's limit as x approaches infinity of sine of the floor of x times pi? Well, clearly the floor of x is any integer, and any integer times pi, you take the sine of that, it's always 0. So this is the same thing as limit as x approaches infinity of 0, and this is of course 0. So clearly this limit exists, and although limit as x approaches infinity of the floor of x is infinity. So this theorem is false. So the lesson to be learned over here is never assume that a theorem is true unless you have a concrete proof, or unless you have a proof to prove so. And yep, that would be all. I would leave you with one thing. So what would happen? This is my question for you. What would happen if I modify this question a little bit, and instead of saying let f be any function, I say let f be any continuous function? Would this theorem now be true or false? Let me know in the comments below what you guys think. Just to give you an idea, the floor of x is not a continuous function. If you graph it out, it has a discontinuity at every integer. The floor of 1 is 1, and anything below that, so it's going to look something like this. So it says 0. At 1 it has a hole. Let's say this is 1, and then from 1 to 2, for example, it's a straight line. At 2 it has a hole, and then at 2 it's 2, and so on. So this is not a continuous function. But what would happen if I modify this question and say let f be any continuous function? Then is this theorem true or false? Do let me know in the comments below what do you think, and I'll see you in the next video.